just as with the Helmholtz energy, we can get a little bit of additional information from the Gibbs energy as well, related to work. Slightly different though. So again, we're looking at constant temperature and pressure process. That's whenever we're thinking about Gibbs energy, that's sort of that's the constraints that we're working under. And just as a reminder, G equals U minus TS plus PV. That's one way we can write it out. So let's go ahead and look at the differential of this, dG. All right, so we'll get du minus TdS minus SdT plus PdV plus VdP. Okay, but we can go ahead and use the first law of thermodynamics to make a substitution here for du. Right, we know that du is equal to TdS. Right, that's Q reversible, minus the reversible work, or sorry, plus the reversible work. Right, so we can go ahead and make that substitution. dG is equal to TdS plus dW reversible minus TdS minus SdT plus PdV plus VdP. All right. We can start canceling some things now. So our TdS terms here will cancel. We're at constant temperature and pressure, so this term goes to 0 and this term goes to 0. And so what we're left with is that dG is equal to dW reversible plus PdV. Okay, and so this doesn't seem, we're close to what we had with the Helmholtz energy, where we have the Helmholtz energy was equal to the work. But we have a slight difference here. We have this plus PdV term. So let's think about this. So the reversible work, this is any type of work, right? So nothing in here was defined in terms of only having pressure volume work or only having an ideal gas or anything like that. This is general, everything we've derived up to this point. So if we subtracted out the pressure volume work is given by minus PdV, right? That's equal to the work from pressure volume, right? From gases moving and pushing on things. So if we subtract minus PdV, we get dW reversible plus PdV, which is what we have here. And so what delta G is equal to, dG is equal to dW non-PV, right? So we subtracted off the pressure volume work, and so we're left with the work that is non-pressure volume work. All right, again, this is for a reversible process at constant temperature and pressure, right? That's all the assumptions that go into here. So it would be things like electrical work or other things. And so this tells you what's the maximum amount of work, right? If we consider an irreversible process, it'll be just like the Helmholtz energy, right? This tells us the maximum amount of work we can get out of our process. The ideal maximum. Obviously, if there's any non-ideal parts of this, we won't get that maximum value. But this would be the maximum non-pressure volume work we can get from our process. So this can be useful if you're considering making a battery or something like that. That's usually done at constant temperature and pressure. And so what's the maximum amount of electrical work you can get out of your system? Delta G tells you that. Or if delta G is positive, right? So this is for negative values. For positive values, it tells you what's the minimum non-pressure volume work required to drive the process. All right, so that's one additional piece of information we can get from delta G. Most of the time we'll be looking at spontaneity and equilibrium, but this is also another piece of information that you can get.